I have to call roll first, sorry. Mark the roll. Okay, Walter. Got it. Okay. Gavin not here yet. Dawson is here. Andrea is here. Josh is here, right? Jake, not here yet. Allison is here. We haven't seen J.D. Williams from the beginning, so we don't know if we're going to see her. Chris is not here yet, and Jalen is not here yet. 5, 4, and 1 is 5. Got it. Okay, now. Okay. Two announcements. The first is pretty important. It pertains to today, and as far as I know, today only. They are going to be testing our fire alarms all day today. So if you hear the fire alarm go off, it's not a drill, it's not a fire, okay? Not a fire drill, it's just testing alarms. So we're not going to be evacuating the building or anything like that. It would not be a bad idea for to have a fire drill or two, but if you hear them today, that's not what this is all about. So stay where you are unless you hear someone running up and down the hall. No, this is real. Get out. You know, this is. So if you hear the alarms go off, not to worry today. Okay. The second is, I think I announced it last time. Can't remember for sure. Not next week, but the following week. That's the 17th through the 20th, Monday through Thursday. That week is Cougar Connection Week. Now, they gave me this tiny little compressed thing that I can hardly read, but there are events going on every day, Monday through Thursday of next week, okay? Both campuses on Monday, Tuesday, and Wednesday, only on Birmingham campus on Thursday. There's things like Constitution Day, when that's going to be pretty interesting. Volunteer fair, these kind of things. The companies or businesses or nonprofits that are going to either be here or have opportunity for sign up or own this thing too. Quite a list of them. Okay. There's also activities within the campus, such as ambassadors, athletics, fine arts, honors college, PBL, Scholars Bowl, SGA, speech and drama, student support services, and STEM program. Those will all have opportunities for you to join any of those as well. So that's coming up not next week, but the following week. I'll go over more detail next Thursday, okay, as it gets closer. All right, any questions on anything we've done so far? Okay. If not, we're starting from the current slide. Actually, we're not starting from there. We're starting at 4.2 exercises the vocabulary. Now, some of you have books and some may not, so listen up as I read these. Each real number t corresponds to a point xy on the blank blank. Unit circle, good. Number 2, a function f is blank when there exists a positive real number c such that f of t plus c is equal to t for all the t's in the domain of f. If you sum real number c, that anytime if this is f of t right here, if you add c to t, you're going to be right there at the same f of t. Okay? And add it again, right there. What kind of function is that called? It has nothing to do with the little dot right here, but it has the same name. All real numbers? No, the dot. Period. So it's called a what kind of function? Periodic function. Okay. That's done visually. Okay, the smallest number c for which a function f is periodic is the blank of f. Period of f, exactly. Okay, that's called the period. The smallest one of those c's, that's called the period. Okay, number 4. A function f is blank when f of minus t is equal to minus f of t. F of minus t is the opposite of f of t. The function is odd. It's an odd function. And blank when f of minus t is equal to f of t. Even function. All right, good deal. Period. Okay. All right. All right. So I already gave all the homework exercises there. Let's get started in 4.3. Okay. Again, we're doing chapter 4, trigonometry, which is the triangle measure of triangles, but we haven't even touched the triangle yet. We've been dealing with unit circle. However, 4.3 is going to get to right triangles, so now we're really going through trigonometry with triangles. Yes?
When we take tests and stuff, do we get a study guide?
Basically, what I suggest for the study guide, and that's a great question, if I make up something for you, then you look at that and you find it fairly passive. So what I suggest is you develop your own study guide, and that makes it active. And I think you'll find it. But guess what? It's open book.
Oh, it's open book?
Yeah, it's take-home test. So, no, I'm not going to give you anything. Okay. All right, here's Kevin. All right.
Do you know when the first quiz or test will be?
The first test is when we finish 4.4, and we're on 4.3 now, so it's coming up fairly soon. Probably next week, I'm guessing. Okay? So, still missing Jake and Chris. Okay? Chris, yeah, Chris. All right. All right, so right triangle trig. Okay, trigonometry. For our objectives here, we're going to evaluate the trigonometric functions of acute angles. Now, what are acute angles?
Less than 90.
Yes, between 0 and 90 degrees, or 0 and pi halves. Okay? And we'll use a calculator to evaluate trigonometric functions. We'll use fundamental trigonometric identities. Later, next chapter, we'll do lots of identities. And then we'll use trigonometric functions to model and solve some real-life problems. Okay. So, let's start with the 6 trigonometric functions. Now, we already know those on the unit circle. Was there a question?
I was telling you what the 6 was.
I'm sorry?
I was saying what the 6 was.
Yeah. Yeah, well, yeah, sine, cosine, tangent, cotangent, secant, and cosecant. Okay? 6 trigonometric functions. We've identified those on the unit circle, but that is a very limited special thing. This is Chris, right? Okay.
You got me too, though.
Yeah, I got Gavin. Yeah. And he disappeared, though. Okay. But Jake is the only one, and he usually comes in. Well, I think there may be a meeting this morning, so I don't know for certain if he's going to make it or not, because 2 baseball players had to leave my first class because they had some meeting they had to go to. So, in this section, we'll introduce trigonometric functions from a right triangle perspective. No longer stuck on the unit circle. It can be any right triangle. Huge right triangles or tiny right triangles. It doesn't matter. We're not limited to the circle of radius 1. Consider this right triangle here with one acute angle, okay, labeled as theta. The other one is also an acute angle, but it doesn't have a label. What is this one? A right angle. That's what that square symbol indicates. For it to be a right triangle, it must have a right angle. Okay? So one acute angle labeled theta shown below. Now, relative to that angle theta, not the other one, not the right angle, that angle theta, we can name these three sides. Okay? Relative to this angle, we call this the adjacent side. Now, sure, the hypotenuse is also adjacent, but the hypotenuse is the hypotenuse. We're going to leave it at that. This is the side that's adjacent to the angle. This side is not touching that angle, so we call that the opposite side. And then, of course, the long side, the side opposite the right angle, is always the hypotenuse. Okay. Now, why did I say the long side? We already said this is an acute angle, and by definition, this also, and now we have perfect attendance. Way to go, folks. Was there a meeting this morning? Oh, the two ball players from my first class had to leave.
What time?
Just about ordered till the end of class. Okay, all right. All right. I thought you might have to be late because of the meeting, but maybe there's had nothing to do with the thing now. I don't know. Okay. So those are the three sides of any right triangle. Opposite the right angle is the hypotenuse. Now, why did I say that's the long side? This is an acute angle. What does that make this angle? Acute also. Why? The three sides of the triangle have to add to 180 degrees or pi. And if that's 90 or pi halves, then the sum of these two is 90 or pi halves. So if the sum is 90 or pi halves, they both have to be acute. Okay? Or, acute. Okay, so since these are both less than 90 or pi halves, this is the largest angle, and always the largest side is opposite the largest angle. If this was the smallest angle, looks like they're pretty close to the same size. Oh, well, that might be a little smaller. If that's the smallest angle, that has to be the shortest side. If that's the middle angle, that has to be the middle angle. Okay, whatever. Okay, so the side opposite the right angle is always the hypotenuse, and then the angle that you've named has an adjacent side to it and the opposite side to it. Okay? Now, with those three names, you can give the trig functions, all six trig functions of that angle theta. And here's how we do it. Using the lengths of those three sides, you can form the six ratios that define the six trigonometric functions of the acute angle theta. And these, again, I don't like the way they do it. Sine, cosine, tangent, cotangent, secant, cosecant. Okay? And here's what they are. Now, this is angle theta. It's always an acute angle between 0 and 90 degrees. The sine is always the opposite side, the ratio of the opposite side to the hypotenuse. So, okay, you've got Sakatoa, right? Yeah. Okay. Cosine is adjacent over hypotenuse, tangent is the opposite over adjacent. And then remembering from before, the cotangent is reciprocal of tangent, so it's adjacent over opposite. The secant is reciprocal of cosine, so it's hypotenuse over adjacent, and the cosecant is reciprocal of sine, so it's hypotenuse over opposite. Okay? So opposite, adjacent, hypotenuse, those represent those lengths. Now, Jalen just said one of the little acrostics that people sometimes use to remember this. And I had a roommate in college when I was in grad school. He was an undergraduate, but he used this one. Let me get my pen set up. Okay. He used sa, ka, toa. And he remembered it that way. To me, I can't tell the difference in sa and ka, which is the A and which is the O. So I just remembered it's opposite over adjacent of hypotenuse is sine, and So anyway, but that's one way to do it. If you find that easy to remember, go for it. It works. See, SOHCAHTOA. Okay. Now, the first time I taught trig when this was Bessemer State Technical College, I was was teaching in this classroom, and a gal that sat right back there, that seat right there, said, "Oh, some old hen caught another, no, I'm sorry, some old hag caught another hag taking oats away." I thought, I've never heard that before, but that's a good way to remember it, okay? Except I really don't like calling people hags, you know. That was only, well, about 2 or 3 terms later, when I was teaching it again, another gal said, "Some old hen caught another hen taking those away." I far prefer hens to hags, so that's the one I remember now. But I just know the sign is opposite over hypotenuse. Cosine is adjacent, and tangent is opposite over adjacent. Okay, and then the reciprocals follow. Okay. Make sense? Fairly easy to remember. Okay? Now, to make the connection back with unit circle, okay? If you think of the unit circle, oh, that's a pretty ugly circle. Radius of 1, and let's deal with just right angles here. Okay, remember the sign was the y value. Why the y value? That's the opposite side, right? And the hypotenuse, though, was 1, right? So that's why in the unit circle, this was just y, this was just x, because the hypotenuse is 1, okay? And then the tangent was y over x. So opposite was the y, adjacent is the x. The difference with the unit circle, the hypotenuse is always 1. So this became 1 over y, 1 over x, and that just became x over y. The adjacent is the x side, and the opposite is the y side. So this is the same thing as before, with the difference being the hypotenuse on the unit circle is always 1. So that's why there were 1s in everywhere you saw a hypotenuse, it was a 1. Everything else followed x and y just like this. Okay? So that's why, to me, it's easier to do right triangle trig first, and then say, okay, same thing as before, just put 1 in for hypotenuse, and you got it for the unit circle. But either way. So let's do example 1. This, by the way, is on page 278, top of the page. Using that triangle, in this figure, figure 420, find the values of the 6 trigonometric functions of theta. So what's the sign of theta? Oh, you got to use Pythagorean theorem first because we don't know the hypotenuse. So what does Pythagorean theorem tell us? A squared, which is, let's count that as the adjacent side, 3 squared plus 4 squared is equal to c squared, but let's call it, well, let's just say that's the hypotenuse squared. Yeah, that's what it is. Okay, so what's 3 squared? Second? 9 plus 16 equals c squared. 9 plus 16 is 25 is equal to c squared. What would c be? 5. Perfect. Okay, so the hypotenuse is 5. And that, by the way, a 3, 4, 5 triangle always works out that way. And any multiple, for instance, a 6, 8, 10, a 9, 12, 15, you know, any multiple of that, you can set up those just like that. Very few triangles will do that, but there are some which are have a special name, I can't think of them now. Perfect square, I think they call them perfect square triangles. Okay. All of them are perfect square, but they're squares of integers. Okay. So, what would your sign be of that triangle? 4 over 5, that's opposite over hypotenuse. What's the cosine? 3 over 5. And what's the tangent? 4 over 3. which again you could do by just dividing that, and you see that works out. What's the cotangent? 3 over 4. What's the secant? 5 over 3. And what's the cosecant? Is 5 over 4. Okay? And again, what I told you before, the sines and cosines are always, certainly in the first quadrant for acute angles, always less than 1 or equal. They can be equal to 1, but most of the time less than 1. And for right triangles, they've got to be less than 1. And the secant and cosecant are always greater than 1. Okay? Tangent, cotangent, flip-flop, they can be any real number. Okay? Sure enough, that's the case. All right. That was easy enough, wasn't it? There is a checkpoint here. I'll tell you on the checkpoint, it won't work out being quite as pretty as the other one was. Now, there's a little historical note here. Georg Joachim Rheticus, okay, way back in the 1500s, was a leading Teutonic, which means basically German, mathematical astronomer of the 16th century. He was the first to define the trigonometric functions as ratios of the sides of a right triangle. So, he's not usually called the father of trigonometry. That's reserved for someone more ancient than him. But he was the first to make those connections. All right. That's how we did it. Let's see how they did it. Erasing those. By Pythagorean theorem, the hypotenuse squared is opposite squared plus adjacent squared. So therefore, the hypotenuse would be the square root of the opposite squared plus adjacent squared. It doesn't matter. You could have said adjacent squared plus opposite squared. It doesn't matter at all. But anyway, it's 4 squared plus 3 squared. Square root of that is square root of 25, which is 5. So now we know all 3 sides of that triangle. 6 trigonometric functions. For theta would be sine of opposite over hypotenuse, which is 4 over 5. The cosine adjacent over hypotenuse, 3 over 5. The tangent is opposite over adjacent, which is 4 over 3. And then they jump up and do the cosecant, I think. Yeah, cosecant is hypotenuse over opposite, which is 5 over 4. Or easier to be, rather than saying that, it's reciprocal of sine. Just think it that way. And secant would be hypotenuse over adjacent, or reciprocal of cosine, 5 over 3, and the cotangent is adjacent over hypotenuse, which is the, reciprocal of tangent. Ooh. I'm fighting it today, folks. I was on the Birmingham West campus until almost 10 o'clock last night, finishing up contracts and dealing with a kid that got his keys locked in a room, and we couldn't get the room open, so it was a late night, and I'm dragging today. Not that y'all care, but just to explain my drowsiness. Okay, so in example 1, let's see. Let's go back and do examples 2 and 3 before we hit that. They show up in the book that way. So let's do examples 2 and 3 before we move on to page 279. Okay. Now, find the values of sine 45 degrees, cosine 45 degrees, and tangent 45 degrees. Okay? Now, what do you know about the angle 45 degrees? That what? Okay, it's acute angle, phi force, and it's exactly a pi force, which is exactly half of pi halves, so it bisects the right angle there. Okay, so this is 45 degrees right there. Now, what else do you know about that? That is on the line y equal x, right? Because it exactly bisects that, so that is the exact diagonal, so your y value is always equal to your x value. So give me a nice, easy number to name the x and y values. 1. I love it. 1 and 1. Okay? X and y are the same, so 1. What does that make the hypotenuse? The square root of 2. Okay? Once you have that, we can find the sine of 45 degrees. And what is that? 1 over root 2. Now, if you don't like radicals in the denominator, how else could you write that? Yeah, and that gives you root 2 over 2. Yeah, root 2 times root 2 is 2. Okay, what is cosine of 45 degrees? One over root 2 again, which is also root 2 over 2. Okay, and what is the tangent of 45 degrees? 1. 1 over 1, which is 1. 1. Okay. All right. So same as it was on the unit circle, it better be. Okay. Those are the values we remember from the unit circle. It's still the values here, and you can see that. And that's usually the easiest way to do that one, is to do 1, 1, and root 2. That's simplest representation of 45 degrees. You could do any multiple of that. 7, 7, and 7 times root 2. That works too. You know, but why do bigger numbers? Okay. Good deal. And that's exactly what we got in the book. They also have a checkpoint there of doing cotangent, secant, and cosecant, which would be pretty easy to do. But if you have problems with it, the audio-video solution for all your checkpoints are at LarsonPrecalculus.com. All right, let's do example 3 before we move on to the rest of that page. Okay. Use the equilateral triangle shown in the figure, and I don't draw equilateral triangles well, but I'll do my best. Let's just assume that those 3 sides are the same. Equilateral. If the 3 sides are the same, what does that tell us about the angles? They have to be the same too. And if they're all 3 the same length, what's the total of any triangle? Say again? 180. So if 3 will go into 180, 60 times. So every one of those is a 60-degree angle. Okay? Now, we're going to use that equilateral triangle and draw its perfect bisector. Okay? Going to bisect that angle exactly, which makes this one 30 degrees and this one 30 degrees. It bisects it, which also bisects the opposite side. Now, that winds up being the shortest side, right? So let's name that 1, 1, and what would these 2 sides be? 2, because 1 and 1 is 2. Those are equilateral triangles. If the bottom of the 1 and 1 is 2, the others have to be 2. Okay? Now we have everything we need to know about a 60-degree or 30-degree angle. Okay? And they're asking for the sine of 60 degrees. Okay, find your 60-degree angle, and what's the sine? Oh, there's one side we left off, the length of that bisect. What is that? that's the say again? The square root of 3. And where does that come from? Because we know that this squared, 4, minus this squared, 1, is equal to that squared. 4 minus 1 is 3. So that has to be the square root of 3. Right? Now we can do the sine of 60. What would that be? Root 3 over 2. Opposite over hypotenuse. What would be the cosine of 60? 1/2. What would be the sine of 30? 1/2 again. Here's your 30 up here. The opposite side of that is 1. The hypotenuse is still 2. So that would be 1/2. And what's the sine of the cosine of 60? Of 30. I can't write. Okay. Cosine of 30 is square root of 3 over 2. That's pretty ugly, isn't it? Okay. Let's see if we can clean that up a little bit. Ooh. All right. Cosine of 30 degrees. Okay. Is square root of 3 over 2. All right. So there we have those again. Just the same as they were in the unit circle. Same value. Sines of a given angle are always going to be the same, whether you've got a huge triangle, a unit circle, tiny triangle, whatever. Those angles, the sine of that is unique. Okay. And this is what they got in the book, root 3 over 2, 1/2, 1/2, and root 3 over 2. Good. And they have a checkpoint there. And they have you do the tangents of 60 and 30 as well. Okay? So now I think we're ready for this table. In example 1, okay, and the other two too, we're either given or we came up with the lengths of two sides, but not of the angle theta. Okay? Often you'll be asked to find the trigonometric functions of a given acute angle theta. To do this, construct a right triangle having theta as one of its angles. Okay? Yeah, okay. Good news, huh? All right. Here is a table showing our favorite angles. Okay, now we left off 0 and 90, but here are the rest of those. Sine of 30, we already got, was the same, by the way. 30 is the same as pi 6. 30 degrees is pi 6 radians. The sine of that is always 1/2, no matter how big. You could have circles that aren't unit circles, or you can have triangles that are any size. The ratio is always going to be 1 to 2. Cosine would then be root 3 to 2. Tangent would then be of 30 degrees would be 1 over root 3. Because the 2's will cancel out, which is root 3 over 3. Now, going to the cosine, the sine of 45 degrees, which is the same as pi 4, that's root 2 over 2. We knew that from before. We've done it again. And the cosine is also root 2 over 2, and we just did the tangent is root 2 over 2 over root 2 over 2, which is 1. Sine of 60, as we just saw from the leaf of the right, and by the way, 60 is the same as pi 30 radians. 60 degrees is pi 30 radians. That's root 3 over 2, and the cosine of 60 is 60 equal to pi 30 radians is 1/2, and tangent of that would be root 3 over 1, which is root 3. Now, things to note here. How is 30 and 60 related to each other?
They're just flipped.
They're what?
They're like flipped because the sine is the cosine. The sine of.
Well, I'm talking about the angles themselves, 30 and 60. How would you classify those angles? Not the trig functions. You're right on the trig functions. What can you say about 30 and 60? They are. Second? angles, you're absolutely right. What kind of acute angles are very special? What do they have to be?
Oh, they both equal 90.
That add to be 90, and what do we call those angles that add to be 90? Complementary angles. They're complementary angles of each other. Complementary. Complementary. Okay? Now, what you were saying, the sine of 30 is the cosine of 60. In other words, the sine of one angle is the cosine of the complementary angle. Complementary. So that's basically where you get that prefix co. Not exactly the same, but close to it. Cosine 30 is, because 30 is a complement of 60, sine of 60 is the cosine of the complement of 60. Those are the same. Okay? And guess what the complement of 45 is? 45. Sine of 45 is the same as the complement of the cosine of its complement, which is 45, and those are the same. Now that just works. That works for these, but it works for any angle. 20 and 70. 15 and 75. 63 and 27. Doesn't matter what they are. The sine of complementary angle. The sine of an angle is the same as the cosine of the complementary angle. We'll get to that in a bit, but just since it was here on the table, I thought that I'd point that out to you. And here's where they say it. Exactly what Dawson was saying. In the box, note that the sine of 30 degrees is the same as the cosine of 60 degrees, both being 1/2. That occurs because the 30 degree and 60 degrees are complementary angles. And when you're talking about them, let's go back to that triangle. You see the sine of 30 is its opposite over the hypotenuse, but the cosine of 60 is its adjacent over hypotenuse, which are the same sides, okay? So they have to be. The sine of a complementary of an angle is the cosine of the complement of that angle. Every time. Not just for 30, 60, 90s or 45, 45, 90. Any complementary angles that works. Okay? In general, it can be shown that the right triangle definitions that cofunctions of complementary angles are equal. Okay? The cofunction meaning cosine, secant, yeah. That is, if theta is an acute angle, then the following relationships are true. The sine of the complement of theta is the cosine of theta. The cosine of the complement of theta is the sine of theta. The tangent of the complement of theta is the cotangent of theta. The cotangent of the complement of theta is the tangent of theta. The secant of the complement of theta is the cosecant of theta. And the cosecant of the complement of theta is the secant of theta. Okay. The cofunctions, that's how they're related to each other. Always. No matter what the angle is. Those have to be special angles, any angle, any acute angle. Okay? Now, I think they just skipped example 4, okay? Yes. So let's go back and do example 4. Okay. And this is, he didn't show us anything about this. It says, use a calculator to evaluate the secant. This is just sort of blown in here out of nowhere. Of 5 degrees, 40 minutes, and 12 seconds. Now, number one, how in the world are you going to do that? Okay, you got to convert your minutes and seconds to degrees, because the calculator, the argument of a trig function is always in degree mode is always degrees. Okay, so you got to first do that, And then you still aren't going to be able to find the secret key on most calculators. So you need to do a reciprocal of cosine. Exactly. So let's first deal with the getting the seconds and minutes to degrees. Now, there's lots of ways you do that. Here's how I suggest. Let's start with the seconds. 12 seconds, we're going to multiply that by something, maybe two somethings, to get degrees. Okay? Now, notice when I multiply by something, these are conversion factors. This is how I do all my conversions in physics and everything. I do this kind of method. Okay? The first blank is for numbers. So don't worry about the numbers yet. Second blank are for units. We always put the units in their place first. Okay? And then, because we're going from seconds to degree, you might have to do an intermediate minutes. You don't have to, but I'm going to do it that way. So let's first change seconds to minutes. What would be the conversion? Deal with the units first. What goes where? Just the units. Between seconds and minutes, what goes where? One goes on top, one goes on bottom. Which goes where? We're going to convert first the seconds to minutes. So one of those units goes on, say again? Okay, you're putting the numbers first. I say let's do the units first. We want seconds down here and minutes up there. Okay? Why? So the seconds will divide out, right? Cancel out, actually. So you were saying how many minutes in a second or how many seconds in a minute? Say again? Yeah, 1 minute is 60 seconds. Okay? So that got rid of seconds to minutes. So let's get minutes to degree. What goes where? Always put degrees in their place. I mean the units in their place. Which goes where? Minutes to degrees. One goes on top, one goes on bottom. What goes where? Degrees on top, minutes on the bottom. So that's the way you can divide it or cancel out the minutes. Okay? And how many degrees in a minute or minutes in a degree? Help me, help me. Yeah, 60 minutes is 1 degree. There we have it. Okay? So, you multiply numerators, that's just 12. Divide by denominators, that's 3,600. So 12 divided by 3,600 is what? I'm going to write it down here because I don't have room there. 12 divided by 3,600. Anyone got a calculator? It's what? 0, 0, what? 3. Okay, probably some more digits after it, right? Huh?
It's a lot of threes.
Yeah, all threes. Okay, so I'm just going to put a bar over that, meaning 0.00333333. Okay, so we got 12 minutes in degrees now. Okay, let's do the 40 minutes. Okay, 40 minutes, I'm going to multiply by blank blank and give me blank degrees. What unit goes where? Always put the units in their place. First blank is for numbers, second blank for units. Which goes where? Degree and minute, one's up, one's down. You tell me. Help me, help me. Minutes on bottom, degrees on top. That way minutes will cancel out. And how many degrees in a minute or minutes in a degree? 60 minutes in 1 degree. So it's 40 divided by 60. I can do that. That's 0.666666667. Yeah, so I'm just going to put a bar over that. So let's add those two together, and that would be 0.66999999. So you could put a bar over that. I believe that's right, yeah. Okay? So this would be the secant of 5 point, and that's degrees, 6, let's just round it to 6, 7. That's going to be close enough, 6, 7 degrees. Okay? Now, we can't do secant, so what could we do? 1 over cosine of 5.67 degrees. Okay? Do that, and you should have your answer. Anyone got a calculator? Do that. Or you could do cosine of 5.7 and hit the reciprocal key, and that gives you the same thing. Anyone got it yet? Oops. Anyone got it? 1 point. Okay. Are you in degree mode? Yeah, that sounds right. 1.009. Is that what you said?
1.005.
5. That sounds reasonable, and here's why I say it's reasonable. The cosine of 0 is 1. This isn't very far from 0. So the secant of 0 is 1. And as cosine is decreasing, secant is increasing, but pretty slowly. Okay? So that does sound, I didn't know it was increasing that slowly. Yeah, they have 1.004916666666. Okay. Yeah, that's going to be close enough to 1.005. Good deal. Any questions on that? All right. If not, let's move on to trigonometric identities. Okay? Folks, you're going to see these over and over and over again. The next chapter, you're going to be using them till they're coming out of your ears. Okay? So get to know them. Okay? These are pretty key issues. And we've already talked about just about every one of them. So here's what they are. In trigonometry, a great deal of time is spent studying the relationship between these functions, and these are identities. An identity is an equation that's always true. You can have other equations like x plus 3 is equal to 5. That's true only when x equals 2. Let's call it a conditional equation. An identity is something that's always true no matter what value you put in. And I've already mentioned this several times. The sine is the reciprocal of the cosecant, which of course means the cosecant is reciprocal of sine. That's called reciprocal identities. Okay? We just used that when we're calculating secant, 1 over cosine. We've already been using these. And every one of the trig functions is the reciprocal of another trig function. Sine and cosecant go together, cosine and secant go together, tangent and cotangent go together. They're reciprocals of each other. So those are your reciprocal identities. We have 2 others, and I've mentioned both of these before too. When we were calculating tangent, I said it's sine over cosine. Okay? Because tangent, sine was on the unit circle was y, cosine was x, tangent was y over x, which is simply sine over cosine. It still goes in right triangle trig and all of them. The tangent is always sine over cosine, and the cotangent is, of course, the reciprocal of that, cosine over sine. Now, this book calls these the quotient identities. Other texts I've taught from before call them ratio identities. Either one of those is fine. The quotient is a ratio. The ratio is a quotient. So those. Now, here's the others. And these are identities we use anytime you have a square pop into your head. Can we use a Pythagorean identity? Okay? Now, does that look like it came from outer space? Okay? Why in the world would sine squared plus cosine squared always be 1? Well, let's see. Tell me what sine is in terms of our SOHCAHTOAs? What is sine?
Opposite over.
Okay, so this would be opposite over hypotenuse, but we're going to square both of those, so that's sine squared, plus, and what's cosine? Adjacent over hypotenuse, but we're going to square that, so square both of those, and the contention here is that's equal to 1. How and why would that ever be? Well, let's look at that. You have a common denominator, so you can now say opposite squared plus adjacent squared over hypotenuse squared. But what is the square, the opposite squared plus adjacent squared? Does the name Pythagoras ring a bell? What is that? That's the hypotenuse squared. So sure enough, this is hypotenuse squared over hypotenuse squared, which of course always is 1. So it doesn't matter what angle your dot got here, sine squared plus cosine squared is always 1. Okay? Now once you have that, and by the way, that's the key. If you remember that, you've got all the rest of them not. Okay? And it's easy to remember. Sine squared plus cosine squared is 1. It always will be, forever and ever. It's an identity. Pythagorean identity. And that's why, because this came from Pythagorean theorem. Okay? Now, I want to write 2 other forms of this that you might not recognize right out at the top. But all I'm going to do is subtract cosine squared from both sides, and that gives you sine squared theta is equal to 1 minus cosine squared theta, just by subtracting cosines from both sides. Or you could subtract sine squared from both sides and have cosine squared theta is equal to 1 minus sine squared theta. So there you have 2 more Pythagorean identities. Okay? They're just this one rearranged. And we'll be using those quite a bit. Okay? Now, let's go back to our first one. Okay, I'm going to clear those out of the way just because there's not a lot of room to write. Go back to this first one. Sine squared theta plus cosine squared theta is equal to 1. Now I'm going to do something bizarre here. Not too bizarre. I'm going to divide everything on both sides of the equation by cosine squared theta. Right? That should be legal in most states as long as cosine isn't 0. And you can't do that anyway. So as long as cosine squared isn't 0, we can do that. Well, what is sine squared over cosine squared? Tangent squared. What is cosine squared over cosine squared? 1. And what is 1 over cosine squared? Secant squared. There we have this identity. So all you need to know is that, and then you can get all the rest of it. Okay? Now, we can take this one and subtract tangent squared from both sides and have secant squared theta minus tangent squared theta equal 1. Big deal, there's 1. Or we can subtract 1 from both sides and have tangent squared theta is equal to secant squared theta minus 1. So there's 2 more Pythagorean identities that you can have. Or we can divide both sides, everything on both sides, by sine squared theta. And what's sine squared over sine squared? 1. What's cosine squared over sine squared? Cotangent squared. And what's 1 over sine squared? Cosecant squared. There's another one, and then you can subtract, various things from both sides, and you can come up with 2 more. So there's tons of different ways you can express these Pythagorean identities. Get to know them, get familiar with them, play with them some, practice with them. They're very, very helpful, especially in the next chapter. We'll be using them some now, but we will definitely be using them in the next chapter. Okay? Now, here's just a little nomenclature or thing of writing this. Sine squared theta is the easiest way to write this in my mind. That means the sine of theta squared. Cosine squared theta means the cosine of theta squared. The problem with saying it this way, now when you write it that way, it's clear. But when you say it sine theta squared, I'm not saying sine theta squared or sine of theta squared. So to say sine squared theta is obvious. The whole sine function is being squared, not that the theta is being squared. Okay. Writing it that way is clear that theta isn't squared, but when you say it, sine theta squared, where does the square go? On the sine or on the theta? With the parentheses there, you know it's on the sine. If you write it this way or say it this way, sine squared theta, you know the sine's the thing being squared. So I like that nomenclature better. It takes more effort to write that one too. Okay. So let's move on to example 5. Let theta be an acute angle such that the sine of theta is 0.6. Okay? Find the value of cosine theta. If you know sine theta is 0.6, what is cosine theta? So obviously we need some relationship between sine theta and cosine theta. What's one relationship we know? Think Pythagoras. Sine squared theta plus cosine squared theta is equal to 1. So this is what we're looking for. So we start with what we know. Sine squared theta plus cosine squared theta is equal to 1. Now what is sine theta? They gave it to us. 0.6. So sine squared theta would be square root of 0.6. 0.36, exactly. Plus cosine squared theta, that's what we're looking for, only we're looking for cosine, that's equal to 1. So what can we do to solve for cosine squared? Yeah, subtract 0.36 from both sides. Okay, that goes to 0, and this gives you cosine squared theta is equal to, what's that? Not that hard. What would that be? 0.64. Okay. So now we have to take the square root of both sides. That gives you cosine theta is equal to 0.8. You got it. So there we got it. 0.8. Just from knowing the sine, you can always calculate the cosine. Okay? How about tangent theta? Can we do that? This was the A part. What's the B part is tangent theta. What in the world is tangent theta? Sine over cosine. And we know that sine is 0.6. We just calculated cosine was 0.8. What does that become? .75. Okay, you did it on a calculator, or you did it in your head? Huh? Calculator. That's perfectly fine. Here's another way you could have done that. Just move both decimals one place. 6 over 8 is 3 over 4. Works. Okay. Now, another way, and this isn't how they wanted you to do this, but it is another way you could have done it. 0.6 is the same as 3/5, And that means this is the hypotenuse, that's the opposite side. And from our triangle earlier, if the hypotenuse is 5 and the opposite side is 3, we know this side is 4. Yeah, and there you get it that way. So there's tons of different ways you can do these problems. They wanted you to do this using Pythagorean theorem, the identities. So that's why we did it this way. But it was real easy to do that way too. Okay? Any way you want to, as long as it's right. Okay? So, let's see how they did it, which I think is pretty much the way we did. But let's see. To find the value of cosine, use the Pythagorean identity that sine squared theta plus cosine squared theta is equal to 1. Exactly what we did. So sine was 0.6, so sine squared would be 0.6 squared plus cosine squared equal 1. That would be cosine squared is equal to 1 minus 0.6 squared. Why wouldn't they go and square that? I don't know. And that would be cosine squared is equal to 0.64. Then take the square root of both sides, and you get cosine is equal to square root of 0.64, which is 0.8. Okay. Just like we did. By knowing sine and cosine, it's real easy to get tangent because that's the ratio identity or the quotient identity, sine over cosine, which would be 0.6 divided by 0.8, which happens to come out 0.75. Okay? And you could just move decimals and reduce, and you would get the same thing there too. And then using the definition of cosine and tangent and the angle. Is this something they ask us to do? I don't think so, unless I missed it. No, they just said you could do that. You could. Okay. Using the definitions of cosine, tangent, and the triangle shown, you can get those results. It's 5 this way. I like it better to do 3/5, 4/5, and that would be 5/5. So, which is 1. So that was just something else they showed us. Lots of ways you can do these. That gets you back to the unit circle type concept. Okay, that was example 5. They're skipping 6 and 7. So let's go back and do 6 and 7. Oh man, I'm losing it fast here. Okay. Ooh. If I'm correct, we don't have much longer, do we? Is that right? Ooh, yeah. Let's see if we can get example 6 done anyway. Let theta be an acute angle such that the tangent of theta is 1/3. Okay? Now here's how I would do this problem. This isn't necessarily the way the book's going to do it. If they tell me that, and they say tangent of theta, here's acute angle theta. As soon as they say tangent of theta is 1/3, what am I going to do? Tangent is opposite over adjacent. Write it down. Now, mine's not to scale. It's not nearly to scale. It should be a smaller angle than that. But as soon as I do that, what do I have? If that's a right angle, what is your hypotenuse? Anybody? The square root of 10. Because 1 squared plus 3 squared, that's 1 plus 9 is 10. That would be the square root of 10. Okay? From this point on, you can do anything you want to. All 6 trigonometric functions. That's not how they wanted you to do the problem. However, they said you could do that at the end. okay? But then, to me, this is far easier to do it this way. If theta is an acute angle, tangent theta, such that tangent theta is 1/3, I just draw this and you go, find the value of cotangent theta. What is cotangent theta? Now, you could do that without, if you know that tangent theta is equal to 1/3, you can do cotangent theta without drawing anything. What is cotangent theta? 3/1, because it's reciprocal. So that was easy. But then the secant theta, now this isn't how they're going to do it, but this is one way to do it. What is secant theta? Yes, it is. It's the reciprocal of cosine, which is, and cosine is called another hen, so that would be hypotenuse, the square root of 10, over adjacent, which is 3. You got it. Okay. Now, how they wanted you to do it was knowing the tangent, then using one of your Pythagorean identities. And which one relates tangents and secants together? Remember that? Anybody? 1 plus tangent squared theta is equal to secant squared theta. This, to me, is the longer way to do it. That'd be 1 plus, and tangent squared would then be 1/9 is equal to secant squared. So that would be 9/9 plus 1/9 would be 10/9 is equal to secant squared theta. And then to take a square root, you have the square root of 10 over 3 is equal to secant theta, which is exactly what we got. I find it much easier to do it that way. That's using Pythagorean too. You just use the Pythagorean theorem on your triangle and you got it knocked. This way works too, though. And they ought to work, okay? It all work out no matter which way you do it, as long as you do all your steps correctly. Right? Okay. That was example 6, A and B. A was really easy, just reciprocal, and the B part was using Pythagorean identity, or the way I did it, the Pythagorean theorem. Okay. I think we can probably get example 7 done, don't you? Oh, let's try it. Okay. Use trigonometric identities to transform the left side of the equation into the right side, as long as theta is an acute angle between 0 and pi halves. Okay? So here's the A part. Sine theta cosecant theta is equal to 1. We don't know that's true. Let's use our identities and see if it is true. Now, with something like this, my fallback, my number one thing, if there's not something that's completely obvious, I always get everything in terms of sines and cosines. So sines already in terms of sine and cosine. That'd be sine theta. What is cosecant in terms of sine or cosine? What is cosecant? 1 over sine. And there enough, that's equal to 1 because the sines divide out and you got 1 equal to 1. Done. That was pretty easy. Let's do the B one. Do we have time? I think so. Okay. The B one is cosecant theta plus cotangent theta times cosecant theta minus cotangent theta. They claim that's equal to 1. Well, I don't know. That seems rather bizarre. Now, what would you do to verify that? What I just said before, getting everything in terms of sines and cosines, You could do it, but let's resist that for now. Let's go and multiply them out first. Because that's the sum times the difference of the same two numbers. One expression multiplied by its conjugate. What did that give you? If you multiply those out, you can actually multiply them if you want. You can FOIL them. What does that give you? Cosecant squared theta. Say again. Yeah, well, I'm doing what I'm calling foiling it, okay? Cosecant squared theta, and then you can do the innards and the outers. The outer gives you minus cosecant cotangent. The inner gives you plus cotangent cosecant. Those add to 0. And then it's just minus cotangent squared theta. The question is that equal to 1? Okay. Now, anytime you have squares of trig functions, think which kind of identity? I think this is what you were saying, Pythagorean identity. And let's look at that again. Go to the top of the previous page and look at that last one listed there. 1 plus cotangent squared theta equal cosecant squared theta. What happens if you subtract cotangent squared theta from both sides? You get cosecant squared theta minus cotangent squared theta is equal to 1. Yes, that itself is a Pythagorean identity in one of its forms. So yes, we have done that one. That checks. And speaking of checking, there are checkpoints at the bottom of the page. And as soon as you get out of class and you have some free time, try to do the checkpoints that we've done and see if you can get those to work. So we'll be ready next time to start with applications involving right triangles. All right, let me give you a few homework exercises. Whoa, we came close to finishing 4-3. You can do any of the odds 5 through 9. They're all at Calc Chat, 5's at Calc View. You can do either 11 or 13. They're both at Calc Chat. Do any of the odds 15 to 21. They're at Calc Chat. Do any of the odds 23 to 27. They're all at Calc Chat. 27's at Calc View. Do any of the odds 29 to 35. They're all at Calc Chat. And then do a few of the identities 37 to 41. They're all at Calc Chat. 39's at Calc View. And try to do some of the odds 43 to 51. They're all at Calc Chat. And let's hang off of those and we'll finish up the rest of those next time. Good deal. Any questions? Have a great weekend. That was the other part of the assignment. How will it make a good weekend? Working trig problems. That will make it a wonderful weekend. Yes. Okay. Okay, where do we leave off? Top of this page. So I'm just going to put it there. All right. Have a good weekend.